Class, this toolbox will introduce matrices and show how they can be used with the types of data we commonly encounter in earth and environmental sciences. Alright, let's start off by talking about what a matrix is. A matrix is basically a bunch of vectors of the same size pasted together. The definition of a matrix is an m by n table of real numbers that has m rows and n columns. So basically it's a table. We've all probably used tables in things like Microsoft. Just like vectors are the mathematical language that we use for a list of numbers, matrices are the mathematical language that we use for discussing and manipulating tables of data. Tables are made up of a bunch of entries. We refer to any entry in the matrix based on what row and what column it is. We typically use the terminology listed on this slide for describing the elements in a matrix. In this matrix, element A12 is in the first row and the second column. Element A22 is in the second row and the second column. Element AMN is in the nth row and the nth column. Matrices can be square, meaning that they have the same number of rows and columns, but they don't have to be and can really take any shape. Just like vectors, matrices can serve many different purposes. Let's look at this matrix for instance. It is a 4 by 3 matrix because it has 4 rows and 3 columns. Remember that the ij entry of the matrix is in row I and column j, so the 2, 3 entry of this matrix is in row 2, column 3, and is 16. Similarly, the 4, 1 entry is in row 4, column 1, so it is 18. This matrix could be used to represent many things. For instance, it could be the temperature at 3 different brown pelican nesting sites, measured on 4 different days. We could also use a matrix to encode the length and width for a bunch of penguin chicks that we are monitoring in a penguin colony. If we are working with meteorologists, we might use the 2 matrices above to encode data on the eastward and northward velocities at different points on the map. Note that we could also have encoded the same wind data in 2 other matrices, V and D, that specify the wind speed, V, and direction, D. Matrices can take any sort of dimensions. We could have a 1000 by 1000 matrix, or you could have a 1,000,000 by 2 matrix. However, there are some special sorts of matrices that we give specific names to because they can be quite useful. For instance, a square matrix is an n by n matrix. That means it has the same number of rows and columns. For instance, a 2 by 2 matrix, a 10 by 10 matrix, or the 4 by 4 matrix shown in this slide. Another commonly used type of matrix is a diagonal matrix. Diagonal matrices are a special form of square matrices. Diagonal matrices only have non-zero entries along the diagonal from top left to lower right. All of the off-diagonal entries are 0. Diagonal matrices are useful because you can multiply them by other matrices to rescale the matrix. The identity matrix is a special case of a diagonal matrix. The identity matrix has 1s along the diagonal and 0s everywhere else. The identity matrix is called the identity matrix because if you multiply it by another matrix, you get that other matrix back. The final type of special matrix that I want to mention is a triangular matrix. Triangular matrices come in 2 varieties: an upper triangular matrix, which is shown in this slide, or a lower triangular matrix. Upper triangular matrices have only 0s beneath the diagonal. Lower triangular matrices have only 0s above the diagonal. Triangular matrices can be useful for multiple things. For instance, the triangular matrix shown above might depict the probability that a larval fish will move from one size class to another size class over the course of a week. This matrix suggests that an individual starting off at size class 1 has a 50% chance of staying in size class 1, a 20% chance of increasing to size class 2, and a 1% chance of skipping all the way to size class 3 over the course of a week. Similarly, an individual in size class 2 has an 80% chance of staying in class 2 by the end of the week. a 9.2% chance of growing to size class 3, and a 0.5% chance of growing all the way to size class 4 by the end of the week. Life tables will be triangular matrices if there is no chance of an organism becoming smaller in size, although note that some invertebrates, such as coral, can actually shrink in size, and also if the life table does not include the production of a new size class 1 organisms from reproduction of larger size classes. Scalar addition and multiplication for matrices is basically the same as scalar addition and multiplication for vectors. For scalar addition, you simply add the scalar to each index in the matrix. So as shown in the top equation, matrix A plus scalar B will now have entries A11 plus B, A12 plus B, A21 plus B, A22 plus B. For scalar multiplication, you simply multiply each entry in the matrix by the scale. So as shown So as shown in the second equation, scalar C multiplied by matrix A will give you the entries C times A11, C times A12, C times A21, and C times A22. Addition of two matrices is also very similar to addition of two vectors. You simply sum the corresponding elements of the matrices to determine the new matrix. Like for vector addition, matrix multiplication only works if your vectors are the same size. In this example, for instance, the element in the bottom left of the new matrix is equal to the element in the bottom left of the first matrix plus the element in the bottom left of the second matrix. Multiplication of two matrices is more complex. It only works if you have two matrices such that the number of columns in the first matrix is equal to the number of rows in the second matrix. The product of the two matrices is determined by summing the elements in one row of the first column multiplied by the elements in one column of the second matrix. Basically, each element is determined by the dot product of appropriate row from matrix 1 and column for matrix 2. For instance, the element in the top left of the new matrix, or in other words, element 1, 1, will be the dot product of the first row of matrix 1 times the first column of matrix 2. It is thus equal to A11 times B11 plus A12 times B21. Let's now also look at how we would calculate, for instance, the element in the second row and third column of the new matrix. It will be equal to the dot product of the second row of matrix 1 and the third column of matrix 2, and hence is equal to A21 times B13 plus A22 times B23. We can also write out how to calculate each element in the new matrix using the following formula. If A is an m by n matrix and B is an n by p matrix, then element Cij in the new matrix C will be equal to the dot product of row I of matrix B multiplied by column J of B. In this equation, the little t following the parenthesis indicates to take the transpose of the matrix. A matrix transpose is found by flipping the rows and columns of a matrix. You can see in this example that if the first column of B is equal to 1, 2, 3, then the first row of B transpose will be equal to 1, 2, 3. Okay, let's talk about an example where you might want to use matrix multiplication. Let's say you've gone to a third world village in maybe Africa or India, and you're trying to convince them to switch to solar power instead of burning wood for energy. You know this will be much cleaner, but you need to also show them that it can be reliable. 4 of the villagers have offered to let you put solar panels on their roofs, and you know that this is an effective solution because it doesn't require using any extra land for power generation. But you need to decide what the best placement of the solar panels would actually be. Like all environmental scientists, your funds are limited, and you've only got 20 panels that you can use for the entire village. So your first step is to go out and measure the light availability at each of the 4 houses. But since one of the main issues with solar power is that power generation is not constant throughout the day, you don't measure it at just one time. You measure it throughout the morning, during the middle of the day, and again in the evening on the roof of each house, since you know that each house will vary based on the slope of the roof, how many trees are around, and where those trees are, etc. You now encode this data in matrix L. Matrix L now shows you the average light levels for each house in the different rows. The columns correspond to morning, midday, and evening light values. Your next step is to postulate some different potential configurations. Matrix P here has different potential configurations you could have for the solar panels. You know that you only have 20 solar panels to use for the village, so each row has a total of 20 solar panels. But each row also has different configurations of those panels. In configuration 1, you put 5 panels on each house. In configuration 2, you've put all of the panels on house 1. If we look at configuration 7, you've put 6 panels on house 1, 12 on house 2, 2 on house 3, and none on house 4. Now, since you know a bit about matrix multiplication, you know that you can calculate the total power generation for the village throughout the day by using a bit of matrix algebra and multiplying P times L. So how do we go about calculating this? Alright, we want to multiply P times L. We know that P is a 7 by 4 matrix and L is a 4 by 3 matrix, so multiplying them together will yield a 7 by 3 matrix. That 7 by 3 matrix will have elements E11, E12, E13, E21, etc. So let's go about calculating the first element of the matrix, element 11. The first element will be equal to the first element of the first row of P multiplied by the first element of the first column of L. So that is 5 times 12, plus the second element of the first row of P times the second element of the first column of L, plus the third element of the first row of P times the third element of the first column of L, plus the fourth element of the first row of P times the fourth element of the first column of L. Let's take a second and actually think about what we're calculating here. Just to make things a little easier to see, I've now similarly color-coded the elements from L and P in the matrices on the top right, where you can actually be reminded what data was in each matrix. So the blue part of this sum corresponds to the number of solar panels on house 1 according to our configuration 1, multiplied by the light level on house 1's roof in the morning. The orange part of the equation now corresponds to the number of solar panels on house 2 according to configuration 1, multiplied by the light level on the roof of house 2 in the morning. I don't have room to show it on this slide, but the green and brown parts of the equation are the corresponding products for house 3 and house 4. So really what all of this element 11 is telling us is the sum of all the electricity generated by the 4 houses in the morning if we distribute the solar panels according to configuration 1. So now if we actually calculate that out, we find that energy generation in the morning will be equal to 350 according to configuration 1. Next, let's calculate element 12. We know that element 12 will be equal to the dot product of the first row of matrix P multiplied by the second column of L. It is thus equal to 5 times 50 plus 5 times 56 plus 5 times 44 plus 5 times 52. Now if we think about what this matrix actually means, we can see that we are calculating the dot product of the configuration 1 solar panels multiplied by the midday illumination on the houses. So we're really calculating the power generation at midday if we position our solar panels according to configuration 1. Once we calculate this, we find that using configuration 1, our midday power generation will be equal to 1010. Let's get through the example of calculating one more element. This time we'll look at element 7.3 in the bottom right corner of the matrix. We know that element 7.3 should be calculated by computing the dot product of the 7th row of matrix P multiplied by the 3rd column of matrix L, so it is equal to 6 times 25 plus 12 times 30 plus 2 times 23 plus 0 times 2. We can also clearly see that this element will correspond to the energy generated in the evening using configuration 7. And if I calculate this out, we can see that if we put the solar panels out according to configuration 7, In the evening, we will have energy generation of 556 in the evening. So now let's generalize for a moment. We don't need to work through every element of this matrix to see that the different columns are corresponding to the morning, midday, and evening, while the different rows are corresponding to our different configurations of solar panels on the houses. If you just for a second compare the labels on matrix E to the labels on matrices P and L, you'll note that the rows of our new matrix E correspond to the rows of P, which was the first matrix that we are multiplying. Similarly, the columns of the new matrix E correspond to the columns of the second matrix L. Further examining this matrix, we can see that this new matrix is giving us some really useful information. If I save us some time and just calculate all the rest of the elements using a computer, we will have most of the information we need to make an informed decision about where to place the solar panels. We now have the information to see, based on the different configurations of solar panels, how much energy is generated at different times of the day. Our next step should be to figure out what we want to prioritize. If our goal is to simply maximize the amount of energy generated, we could take the sum of each row to see which configuration gives the most energy throughout the day. This might not actually be what we're most interested in, however, especially if we don't have a lot of battery power. Maybe the residents of the village really need to prioritize energy availability in the evening when they come home from work, while also ensuring that there is a minimum amount of energy available in the mornings. By comparing the different entries in our new table, we can help them make an informed decision about the best placement of solar panels. Alright, since matrix multiplication really is very important, let's go through one more example. This time we'll talk about the diets of petrels. Maybe we've been studying a colony of petrels and we found that their populations have been declining. One hypothesis we have is that they aren't getting enough food. We know that they need to get carbon, nitrogen, and phosphorus from their diets. So we design an experiment to figure out how much carbon, nitrogen, and phosphorus they're getting from their food. First, we go into the colony and catch 4 birds. We force them to regurgitate their foods, and yes, this is something we sometimes do when studying seabirds. When they regurgitate their food, we sort through it, and we're able to look through this partially digested muck and identify the different zooplankton they're feeding on. We find that the main organisms in their diets are all open ocean crustaceans: krill, copepods, and hyperiid amphipods. In matrix A, we encode the abundances of krill, copepods, and amphipods that we identified in the guts of each of the birds. Unfortunately, we can't really determine the carbon, nitrogen, and phosphorus that they've consumed from these organisms directly from the contents of their guts, because these prey are already partially digested. The birds may have already extracted a lot of the carbohydrates and protein from their prey. So instead, we're going to go back out, put some nets in the water to collect healthy krill, copepods, and hyperiid amphipods from the environment. We then measure the average carbon, nitrogen, and phosphorus content of each taxon that we caught, and we encode it into matrix E. In matrix E, the rows correspond to the elemental composition of krill in the first row, copepods in the second row, and amphipods in the third row. The columns correspond to the elements in each type of organism. The first column is carbon, the second column is nitrogen, and the third column is phosphorus. Now if we multiply A times E, we can get a new matrix D that will correspond to the amount of carbon, nitrogen, and phosphorus in the diets of each of our petrels that we sampled. Remembering back to how the first matrix multiplication turned out, we might surmise that our columns of the matrix correspond to the different columns of matrix E, or in other words, carbon, nitrogen, and phosphorus, while the rows of the product matrix will correspond to the rows of the first matrix, or in other words, bird 1, bird 2, bird 3, and bird 4. Okay, so that is what we might assume, but you know what they say about assumptions. It's a good idea to make assumptions as long as you always make sure to test them. So let's calculate the first element and see if it is what we think it should be. Now if we multiply A times E, we can get a new matrix D that will correspond to the amount of carbon, nitrogen, and phosphorus in the diets of each of our petrels that we sampled. The first element is the dot product of the first row of matrix 1 multiplied by the first column of matrix 2. so it is equal to the first element of row 1 of matrix 1 times the first element of column 1 of the second matrix, or in other words 12 times 4.2, plus the second element of the first row of the first matrix times the second element of the first column of the second matrix, plus the third element of the first row of the first matrix times the third element of the first column of the second matrix. So if we now take a look again at the matrices on the top right that have all of our columns and rows labeled, we can see that we are multiplying the amount of krill eaten by petrol 1 by the amount of carbon in a typical krill, plus the amount of copepods eaten by petrol 1 times the carbon in a copepod, plus the amount of amphipods eaten by petrol 1 multiplied by the carbon in an amphipod. And, based on what we assumed our new matrix D should be, the element D11 that we just calculated should be the carbon consumed by petrol 1. So that makes a lot of sense. And if we calculate it out, we find that petrol 1 consumed 105.4 milligrams of carbon. Just for practice, and to make sure that our assumptions really are correct, let's calculate one more element. Let's pick D32. Element D32 will be equal to the dot product of the third row of matrix 1 multiplied by the second row of matrix 2. It is thus equal to 22 times 0.7 plus 44 times 0.08 plus 23 times 0.02. And if we look again at the rows and columns in our labeled matrices on the top right, we can see that this is the diet of petrol 3 multiplied by the nitrogen contained in each prey item. So that again makes sense since we think this element should be the nitrogen contained inside petrol 3. I can now calculate that value for us, and it is 23.52. If I quickly finish the matrix multiplication using a computer, sorry, I had a technical glitch there for a second. Let's try this again. If I quickly finish the matrix multiplication using a computer, we can see the amount of carbon, nitrogen, and phosphorus consumed by each of the petrols. This is now some very powerful information that allows us to test some of our hypotheses about what might be affecting these birds. For instance, if we can determine how much carbon, nitrogen, and phosphorus they actually need, we can determine which element is likely to be limiting. We can also figure out whether these petrels are likely to be food limited, or whether we should attribute the decline of the colony to some other driver. Matrix multiplication is very important, and I know that it can initially seem a bit mysterious, so I want to just make it clear how you can always remember which rows and columns you need to multiply to create the product matrix. The first thing that you need to remember is that you always multiply a row from the first matrix by a column in the second matrix, row by column, RC like RC Cola. After that, everything is pretty easy. An element at the top is going to get the top row, and an element on the left is going to get a left column. So the top left element, 1, 1, is the dot product of the topmost row of matrix 1 and the leftmost column of matrix 2. The bottom right element will get the bottom row and the rightmost column. The element 4, 2 is in the fourth row, so it'll get the fourth row of the first matrix, and it's in the second column, so it'll get the second column of the second matrix, and etc. for the rest of the elements. That's it for this toolbox. Don't forget to take the mini quiz on Canvas that goes along with this toolbox.